This beachgoer obviously feels a bit cold, yet the sand is uncomfortably hot for walking with bare feet. How can the air be so cool and the sand be so hot? A day at the beach can mean fun and relaxation. It can also provide an informative study of heat transfer concepts. The cool, stiff breeze that blows off the ocean is the result of convective heat transfer in the air caused by the warm landmass and the cool ocean water. Although the air is cool, the sand is too hot to walk on with bare feet. Radiant heat transfer from the sun through empty space warms the earth, especially the sand on this beach. A pair of rubber sandals are needed to walk across that hot sand. The rubber material is a poor conductor of heat compared to skin, so feet stay comfortable despite the high sand temperature. After a little more basking in the radiant warmth of the sun, we shall delve further into the physics of heat transfer. We have already learned that heat flows from a region of higher temperature to one of lower temperature. How is the heat transferred? One way is by a process known as heat conduction. Remember that when an object is heated to a higher temperature, its molecules move around more vigorously. Heat conduction can be visualized as the transfer of heat energy from the hot end of an object to the cold end of an object via molecular collisions along the object. The rate of heat flow through an object is proportional to the temperature difference between the hot and cold ends. The standard units used for heat transfer are joules per second. The thermal conductivity of a substance is a measure of its ability to transfer heat by conduction. Which of the following materials do you think has the highest thermal conductivity? Correct. Metals such as copper have very high thermal conductivities. Materials with high thermal conductivities are called good heat conductors. Materials with low thermal conductivities are referred to as insulators. Metals are good conductors because they have a lot of free electrons bouncing around that aid in transferring the heat energy. In the United States, insulating materials are given an R value. The larger the R value a material has, the better the insulator it is. If you want to save the most money on home energy costs, which ceiling insulation? Incorrect. To save the most money on energy costs, you want the best insulation. This is not the best insulating material. Try again. Incorrect. To save the most money on energy costs, you want the best insulating material. This is not the best insulating material. Try again. Correct. To save the most money on energy costs, you want the best insulating material. The best insulating material is the fiberglass roll because it has the highest R value. Liquids and gases are generally poor conductors of heat relative to solids. The molecules that make up liquids and gases are usually farther apart than those in solids, and therefore they can't interact as well to transfer their heat energy. As we shall see in a later section, liquids and gases can transfer heat energy more effectively by another method. Have you ever wondered why the colorful blobs of lava in a lava lamp continually go up and down? We can see that conduction of heat through the base warms the lava. However, that doesn't explain why the blobs of lava move up and down. What causes that? The reason is convection. Convection involves the transfer of heat by the mass movement of molecules from one place to another. The lava is heated near the base of the lamp, and the heated lava blobs rise upward because they are less dense than the surrounding liquid. The rising blobs cool, thereby increasing their density to the point where they eventually sink back down to complete the cycle. We see examples of convection all around us. A pot of water used for cooking heats up more effectively due to convection currents in the water. A furnace heats a home more effectively by forcing a convective cycle through the use of a fan and hot and cold air registers. Convective heat transfer can occur at the interface between a solid object and a fluid or gas. Newton's law of cooling states that the rate of heat loss is proportional to the temperature difference between the object and its surroundings. Suppose we take some cookies out of a hot oven at 200 degrees Celsius. Will the cookies cool off faster in the kitchen at 25 degrees Celsius or in the dining room at 20 degrees Celsius? Correct. The temperature difference between the cookies and the surrounding air is greater in the dining room. Therefore, according to Newton's law of cooling, they will cool faster in the cooler dining room. It is important to note that conduction and convection both require interactions with matter in order to transfer heat energy from a hot to a cold region. The vanes of a Crookes radiometer spin when heated by a light source which is not in physical contact with it. How do you think the light source transfers heat energy to the radiometer vanes? It transfers heat by radiation. Radiant energy transfer involves the emission and absorption of electromagnetic radiation, and therefore does not require a medium for heat transfer to occur. A hot body such as the sun emits radiant energy. The peak frequency of the radiant energy is proportional to the temperature of the body. When another body absorbs the radiant energy from the sun, some of that energy is converted to heat. The radiant energy from the sun that is mainly responsible for heating the earth is infrared radiation. Darker objects are better absorbers of radiant energy than are shiny objects, which reflect much of the radiant energy. A good absorber is also a good emitter. An ideal body that is a perfect emitter or absorber is known as a black body. The temperature difference between an object and its surroundings determines whether the object is an emitter or an absorber. If the object is at a higher temperature than its surroundings, then a net flow of radiant energy will move from the object to its surroundings. If the object is at a lower temperature than its surroundings, then a net flow of radiant energy will move from the surroundings to the object. Is a person standing in a room at 20 degrees Celsius a net emitter or a net absorber of radiant energy? Incorrect. The person is not a net absorber of radiant energy. Try again. Correct. Because the body temperature of humans is about 37 degrees Celsius, which is higher than the surrounding air temperature, the person is a net emitter of radiant energy. It is important to note that heat transfer in the real world often occurs via more than one process simultaneously. Let's look again at our lava lamp. Heat is conducted through the base to the cool lava. The hot lava blobs rise and transfer heat to the top of the lamp via convection. The hot lava blobs cool by radiating heat to the room and then sink back to the bottom of the lamp.